3. But before we get into the material, I want to talk a little bit about our schedule for the next little bit. So today and Friday, today, which is lecture 17, and the next lecture, which will be 18, we'll cover chapter 3, and then we will be done with chapter 3. In chapter 3, we are only doing the first 5 sections. If you look at the index of your book, you'll see that only the first 5 sections are non-asterisked, meaning that the remaining sections are optional. And so we will not cover those in this class. You may cover that material later in a more advanced mechanics of materials class, but for now, sections 1.3 through 1.5 will be the content. So that will be lecture 16, 17, and 18. Then we will begin chapter 4. In chapter 4, we talk about a very specific type of deformation, which is a pure bending moment. And once again, there are several optional sections in chapter 4, but we will only cover sections 4.1 through 4.5. So that will almost assuredly be lectures 19, 20, and 21. Now, the reason I'm going through this schedule right now with you is we are on the verge of starting to talk about when our midterm exam will be. So what happens is that today in this class in real time, perhaps not if this is being broadcast at a later date, but today is Wednesday, October 3rd. So this would be the day that we would have lecture 17, and then lecture 18 would be on Friday. Lectures 19, 20, and 21 would then be on Monday the 8th, Wednesday the 10th, and Friday the 12th. So what that means is the following week, on the 15th, instead of having, the next scheduled lecture would be 22, but in between 21 and 22, we're going to take a pause and we're going to do a review for the midterm exam. And then in this class, our lecture, our midterm would be probably on October 17th, or in other words, after lecture 21 is in the can. So just letting you know, we're going to have, of course, a homework assignment for chapter 3, and then we'll have a homework assignment for chapter 4. We will have a day of review so that you'll have an opportunity to ask questions. If you're in class with me physically, we can do that in class, and I will vodcast that for your classmates who are not in here physically. But then after we finish that review, then we'll take the midterms. So we're a couple weeks out at this point, but I just want to let you know where we're headed. Okay. So do you guys have any questions? Because it seems like we spent a long time. We have spent much more time on chapters 1 and 2 and the pre-work than we are doing on chapters 3 and 4. But the reason is there's less content in 3 and 4, and we've laid the groundwork for a lot of the things that we need to do. So that's what's going on. So let's continue our discussion in chapter 3. And we are talking about, in both chapter 3 and chapter 4, we talk about a physical effect. In this case, we're talking about torsion, but we limit the geometry of our discussion in order to make the math more doable at this level. So in this section, we talk about torsion, and we are going to talk about power transmission. These are the two topics, and the effects of both on circular and hollow circular shafts only. And the reason, and then, so as I pointed out last time, there are instances, very many instances, where torsion is applied to a non-circular shaft, but we limit this because A, we can get the principles of torsion and the principles of power transmission without getting lost in the weeds of the geometry. So I'm just following the lead of the authors of your textbook on this one, but I do think it's a proper approach. So just briefly what we talked about last time, if we have a shaft that is circular in cross-section And if we consider I don't have a better pen here. Oh, there we go. And if we consider a torque that we apply to this shaft, what will happen is that on the axis of the shaft, that we will move from some point, which was called A, to point A prime, and on the face of the shaft, we will also move from some point A to A prime. And since this arc is the same as this, there is a relationship between the angle of, this is referred to as gamma or shearing strain, this is referred to as phi or angle of twist. And there is a relationship between those two where, based on the length of the shaft and the radius, which is referred to as C, of the face, and that's basically that gamma, or the shearing strain, is equal to rho, which we'll discuss in a minute, times phi over L, and that gamma is also equal to rho over C times gamma max. Okay? Now, when we talk about rho, this is really the important thing from this discussion. When we look at the radius of this circle, here to here, 0 to C, everywhere in between is rho. So what that's basically saying is that, let me just write one more formula over here. Tau then is equal to rho over C times tau max. Okay? Now this is an important relationship because what we're really saying is that the tau, or shearing stress, is a linear function. Tau is a linear function. In other words, it increases from 0 at the center to a maximum at the edge, a linear function in rho. So at 0, it's equal to 0. At C, it's equal to tau max. And everywhere in between, it varies linearly with the distance from the center. Okay. Then sort of the conclusion of this discussion is that tau, shearing stress, is equal to T torque times rho over J, or of course we could say that tau max is equal to T times C over J. And these two formulas are referred to as the elastic torsion formulas, in that they relate the applied torque to the geometry. Both C, rho, and also J are functions of the geometry of this circular section. And so elastic torsion formulas basically tell us that tau is a function of the geometry of that shaft and also of the torque that is applied to it. Now J, we discussed very briefly last time, is referred to as the polar moment of inertia. And it actually, this is actually the reason, this and the warpage, that we only use the circular and hollow circular shafts. But the formula for the polar moment of inertia is the integral of rho squared dA. And we'll never use this in this class. This is true, but we will not use it. We're not going to use this integral. We just know, or I told you, that J is equal to 1/2 pi times C on the outside to the 4th minus C on the inside to the 4th. So if you have a solid circular shaft, this is 0, and otherwise you have to take into account the radii of the outside and the inside if you have some sort of an annular space. Now, another interesting thing we had talked a little bit about ductile and brittle failures, and we'd mostly talked about them in terms of normal stress or shearing stress, and we had said that certain structures fail in normal stress, certain fail in shear. Now, what you need to see when we talk about torsion, torsion does not induce any normal stress at all. It's all shearing stress. So everything that we have is an angular change. But in your textbook on page 157, it would show you what a shaft will fail like if you subject it to a torque, if the material is brittle, or if the material is ductile. And what this really indicates is that this brittle failure occurs roughly on a 45-degree angle. And as you recall, oops, can you even see that? There we go. How's that? So this is this would be a ductile failure. This would be a brittle failure, and the brittle material fails basically on a 45-degree angle, which is the angle of maximum tau that we learned back in chapter 2. All right. So these are some of the ideas that we come up with when we start to work problems. Now, the last little piece of information I want to do before I work a couple of problems for you today is to indicate units on these quantities. We know from past experience that tau is in units of, or let's say dimensions of force per length squared, such as Newton per meter squared, or which is a Pascal, or a pound per square inch. Torque, T, is in units of force times a distance. So it's in dimensions of force times length. So torque can be measured in Newton meters, can be measured in foot pounds. And in the SI system, we would say Newton meter, Newton dot meter, because this is actually from the same integral of del W is equal to F dot D del R. So we have a dot product, so we sort of indicate it this way. It can also be in what are called foot pounds, which are, the correct way to write that unit is to put the unit of force first, but it's still referred to as a foot pound, even though it looks backward. I'm not really picky about that, but I've never heard anybody call it a pound foot if you talk about torque. So just so you know, so you don't sound silly with your more practical colleagues. All right, so let's take a look at a problem. Let's look at problem 3.2 for starters. Okay, 3.2 reads, for a cylindrical shaft shown, so what we have is a base from which a shaft is attached, and we're subjecting it to a torque like this, and we're told that the radius C is equal to 18 millimeters. Okay, and it says for the cylindrical shaft shown, determine the maximum shearing stress, tau max, caused by a torque of magnitude 800 Newton meters. All right, well, what do we know about tau max? If we look at the cross section of that shaft, where is tau max going to occur? Tau is equal to 0. Tau gets bigger until we get to the edge. Tau max occurs at the edge. Okay? So that means that tau max is going to equal torque, which is a constant, times C over J. Right? So tau max then is going to equal the applied torque, which we're told is 800 Newton meters, times C, which is 18 millimeters, or 18 times 10 to the negative third meters, which once again you don't have to do if you're comfortable keeping it in millimeters, but then you have meters and millimeters in the same problem, which is difficult. Then over this quantity J, the polar moment of inertia, which is 1/2 pi times, this is not hollow, so it's just C raised to the 4th power. Okay. So the first thing is, if you look at the units on this, this is going to be meters to the -2 in the top, and TC, no, I'm so sorry. This is meters squared in the top. I was thinking what's going on. And meters to the 4th in the bottom. So meters squared over meters to the 4th is meters squared in the bottom. So it's going to be meters squared. We're left with newtons. And so what that means is it's Newton per meter squared or Pascal, which once again, because a Pascal is tiny, we're probably going to have a whole bunch of them. But let's go ahead and work the problem and find out. So tau max then, this 1/2 becomes 2 in the numerator. 2 times 8 and times 18. We're going to work with the powers in just a minute, divided by pi. Down here, I have 18 raised to the 4th power, right? And then what are my powers of 10? Well, if I take 10 to the -3rd and I multiply, and I raise that to the 4th power, this becomes 10 to the -12th in the denominator, which becomes 10 to the +12th in the numerator. And so I have 10 to the -3rd, 10 to the 12th, which is 10 to the 9th. So once again, there's a whole bunch of them. The other thing is 18 cancels against one of the 18 to the 4th and leaves me with 18 to the 3rd. So in terms of my numeric value, I have 2 times 800 divided by pi divided by 18 to the 3rd power. And then it's multiplied by 10 to the 9th. So I have 2 times 800 divided by pi and divided again by 18 raised to the 3rd power. And that number is 0.087 times 10 to the 9th pascals. So if I move this over, it would be 87 times 10 to the 6th pascals, which is 87 megapascals. Okay. So that's problem number 2. I would like to do another one with a hollowed out shaft so that you can kind of see that, how that works out. And then I will assign the first homework problem. I'll give you a couple little hints and I'll give you a couple homework problems. And then on the vodcast number 18, I'll start on talking a little bit more about gamma or shearing stress on these types of problems. But we're just kind of working with the geometry right now. Okay, so for a hollowed out shaft, I would like to take a look at problem 3.6, which is right here in your textbook, and you can see we have a torque of 3 kilonewton meters applied to a solid bronze cylinder. Oh, it's solid. Wait, the percent of the torque. Sorry, I thought that was hollow. It's not.
Are we going to figure out forces on a drive shaft?
Forces on a drive shaft?
Yeah.
You'll figure out the torques on a drive shaft. Is that what you're asking me?
Yes.
Yes, we certainly will. Torque and force are not the same thing, so I have to flip over into engineering teacher at that point and stand corrected. Let's look at 3.5. We have a 3-inch diameter solid cylinder loaded as shown. Determine the maximum shearing stress and determine the inner diameter of the 4-inch diameter hollow shaft shown, for which the maximum stress is the same in part A. All right, so 3.5 is sort of a double duty problem. The first thing is we compute the stress on the maximum stress on a solid shaft. And then we say, what is if I hollow it out, if I make the shaft a little bigger and hollow it out, what does the inner diameter have to be to carry the same stress? All right, so we have a 3-inch diameter shaft. So C is equal to 3 inches. And it's loaded as shown. It has a torque of 40 inch kips, which is 10 to the 3rd inch pounds, right? Great unit. So let's find, we know that tau max then is equal to TC over J. We know that J is 1/2 pi times C to the 4th for a solid cylinder. So I'm going to reduce that and flip this up. The half becomes 2 in the numerator. So it's 2T over pi C to the 3rd is what this reduces to for a solid cylindrical shaft. So on part A, my tau max is 2 times 40 kilopound, which is 10 to the 3rd pound force inches, divided by pi times C, yeah, I did that right, 3 inches raised to the 3rd power, okay? So the first thing that you can see here is this inch will cancel against these inches to the 3rd to yield inches squared in the bottom. And then on the top, we're going to have 10 to the 3rd, let's put 10 to the 3rd over here, pounds of force. So my base unit is going to be pounds force per inch squared, which is PSI. Numeric value is going to be 80 divided by pi divided again by 9. So 80 divided by 9 and divided by pi is 2.82. So this numeric value is tau max then is equal to 2.82 times 10 to the 3rd PSI, which could also be written as 2.82 KSI. Either one of those answers is acceptable. Now the next part, it says determine the inner diameter of a 4-inch diameter hollow cylinder shown for which the maximum stress is the same in part A. Okay, so what I want to do now is to take a 4-inch diameter shaft, hollow it out, and I don't know what my inner radius is, but I want it to bear this same tau max. So tau max in this case is equal to TC over J, but now my C is 4 inches, but J is going to be 1/2 pi times 4 inches to the 4th power minus that inside diameter raised to the 4th power, and this is the value that I want to solve for. So I start over here and plug in my numbers. 2.82 times 10 to the 3rd pounds of force per inch squared is equal to, what does it ask? Determine the inner diameter. Okay, and we're still applying 40 kips, all right? Equals tau, or T, which is 40 kip inches, okay? 40 times 10 to the 3rd pound of force times inch times 4 inches over 1/2, which becomes 2 in the numerator, over pi times the quantity 4 inches to the 4th minus this unknown quantity raised to the 4th power. So these will cancel out. I have inches squared in the top, inches to the 4th in the bottom. And so what that means is that if I solve for C1, it's going to be inches to, C1 to the 4th is inches to the 4th, just like this. So if I solve for C1, it's going to be in inches. All right, so let's do some math. We get 2.82 times 10 to the 3rd. I'm going to cross multiply, times pi times 4 to the 4th power, which is 256, I believe. Yes. So this is 256 minus C1 to the 4th equals 40 times 10 to the 3rd. 4 times 2 is 8. 8 times 40 is 320. And that is times 10 to the 3rd. Okay, so the good news here is that I have 10 to the third multiplied clean through here and 10 to the third multiplied clean through here, so they cancel out. I'm going to divide over this just to get a constant, so I'm going to divide by 2.82 times pi on both sides. And I'll get over here 256 minus C1 to the fourth power equals 320 divided by 2.82 divided again by pi. And that value is 36.12. So now to solve for C2, I'm going to get another piece of paper up here. Spots. Here we go. 6, yeah, that's about right. Okay. So I'm going to solve for C1 to the fourth by bringing it over to this side of the equation. And that's going to equal 256 minus 36.12. So we get 219.88 is equal to C1 to the fourth. So to solve for C1, I need to take the fourth root of both sides. And I get C1 is equal to, where's my power button? Y to the X. Not familiar enough with my calculator. Where? Oh, there's a fourth root. That'll work. So let's go 219.88. And then let's say fourth root. Oh, sorry, got to do it the other way. So we go 4 second root of 219.88, and that value is 3.85. And because we've kept everything in inches, that would be in inches. So therefore, what we have is a 4-inch diameter shaft, the inner radius of which is 3.85 inches. So this ring of material is actually 0.15 inches wide in order to bear that same stress. Okay. Do you guys have any questions about that? Alrighty. I find often that students and teachers alike have trouble taking roots or doing exponents with units. And so if you don't, congratulations, but it's a place where people do tend to make mistakes. So one place that you might notice if you had made a mistake is if the inner diameter, for example, was larger than the outer diameter. That is not possible. So just something to keep in mind as you're checking your work. All right, well, ladies and gentlemen, that is it for today. So once again, I will do a pre-recording of lecture number 18, and it will be available for you on Friday, if not before. And that will be the lecture in which I finish chapter 3. I'll also post a homework assignment for you, and your homework assignment for chapter 2 is due tonight. So, all right, have a great day, and we will see you on next Monday. But you'll see me on the podcast on Friday.